speaking for us about non-vanishing of Ceresa and gross Kudla Schoen cycles.
Thank you. Thanks, Payman, for the invitation. And I'm especially happy because Payman invited me to give this talk, because you will see in the end that a project I did this summer was really inspired by Payman's work. So today I'll be discussing the topic, which is non-vanishing of Ceresa and the gross Kudla Schoen cycles. And to start discussing this topic, let me start with a quick introduction of algebraic cycles. Here's how I think about algebraic cycles. So the most famous sculptor Michelangelo says that every block of stone has a statue inside it, and it is the task of the sculptor to discover it. And this is how I feel about algebraic cycles. So every algebraic variety has some algebraic cycles in them already. It's not something man-made or we constructed from nothing. Really, it's already there. And I feel the task of the mathematician is to discover these algebraic cycles and to classify them. So for example, I want people to feel that algebraic cycles are extremely natural objects, because we study as algebraic geometers or arithmetic geometers, we study algebraic varieties. And of course, we need to understand the subvarieties in them. So here are some pictures. One thing is you can think about the case of a elliptic curve, or in general algebraic curve, which is a one-dimensional algebraic variety. Then if you want to consider subvarieties, it's like collections of points, right? And then we consider the linear combination. That is actually our very familiar concept of divisors. So in this sense, we have already started algebraic cycles when we started divisors on algebraic curves. Another example, I draw a picture here, is when you go beyond codimension 1. So now I can't draw a complex picture. This is a real picture. Imagine a real threefold. And then the 1 cycles, the codimension 2 cycles are just curves lying inside this threefold. So since we want, as when we started divisors, right, we don't want to treat every point as different. So to classify algebraic cycles, we need to introduce some equivalence relations. And let's just think about the case of divisors on curves. What equivalence relations do we usually use to classify them? Well, linear equivalence, right? So think about the case of divisors on curves. We usually say that they're linearly equivalent if their difference is a principal divisor, right? Another way to think about it is if I can find a map down to P1, and then I say that any two fibers of this map are linearly equivalent. And then we generalize this definition to general algebraic cycles. Namely, we say that two algebraic cycles are linearly equivalent if I can find some map down to P1, and then these cycles are two different fibers. And we take the equivalence relation generated by all the set of maps to P1. So it's not, you don't have to find one map to P1 to identify two cycles. You just need to have a chains of maps to identify them. So it's a relation generated by that. So once we define this linear equivalence, we can define the so-called Chow group, namely the algebraic cycles are already defined as formal linear Z combinations of subvarieties, and which means it's just like the divisor. This is like the divisor group, right? But now if I modulo linear equivalence, I will get the divisor case will get the divisor class group or the Picard group. And here, in general, we will get a Chow group of codimension R algebraic cycles modulo linear equivalence. So the goal today is to discuss cycles in the Chow group. Okay, so how do I study cycles in the Chow group? And for example, study algebraic cycles which are not linearly trivial. Well, we need to linearize it, right? So think about, again, algebraic cycles, one way to think about it is, this is subvarieties, right? In the case of other type of geometry, differential geometry or algebraic topology, right? They are similar as you were studying some submanifold or subtopological space. And we rarely directly starting subtopological space as it is, right? We first step is to study the homology group, the homology class that some subtopological space generates. So instead of directly working with this geometric object, this algebraic cycle, you want to work with some linearized object. So how to get the linearized object is exactly by, again, getting some homological, cohomological classes from it. So there is a natural cycle class map that maps algebraic cycles to a singular cohomology class or any weak cohomology theory really class. So the idea of this map is the following. So I have a algebraic, so my algebraic variety, now let's just think about it over C, okay? And then I have some sub-algebraic variety in there, my algebraic cycle. Now let's just think about complex analytic topology. Then I really have a topological space with this sub-topological space, right? As I already mentioned, then my sub-topological space gives me some homology class, right? I use a singular homology, and then I dualize it, use Poincare duality, I get cohomology class. So that is a very direct way to think about this cycle class map, how to get from a algebraic cycle to a singular cohomology class. But note that the codimension from R becomes 2R because I am in complex analytic topology. So a curve is a Riemann surface, right? Is that gives you H2 class. So any algebraic cycle that lives in the kernel of this map are called homologically trivial because it gives you the trivial homology class. So the idea to think about this, the homologically trivial cycles, again, I will always draw the analogy between divisors on curves, right? It's the same as saying I am starting degree 0 divisors, because this cycle class map restricted to points on curves is nothing but the degree map. Okay, so this is the same as saying I am starting, this really is a pick knot, right? I am starting degree 0 divisors modulo linear equivalence. Okay, so then if I have a degree 0 divisor, how do I figure out whether it is equivalent to 0 or not, right? Well, to classify this set of degree 0 divisors modulo linear class, we have the Arbor-Jacobi map coming from integrals, right? And in this higher dimension case, we can generalize that to also get a higher Arbor-Jacobi map. So it was constructed by Griffiths. So Griffiths' Arbor-Jacobi map maps the Chow group could dimension R cycles modulo linear equivalence to a complex torus. So this is a generalization. It's called intermediate Jacobian. It's the generalization of our very familiar Jacobian variety of algebraic curve. And so this map, unfortunately, has non-trivial kernel, but you can, of course, use this map to detect non-triviality. If the image is non-trivial, it does tell you have a non-trivial algebraic cycle, right? Okay, so this is the complex picture. And if you think about a more arithmetic picture, then consider your algebraic variety was defined over some non-algebraically closed field, for example, a number field. Then in the theory of Vitauco homology, if you have a homologically trivial algebraic cycle, you actually also get a L-adic. So there is also a L-adic Arbor-Jacobi map that gives you a Galois cohomology class. So the idea is you think, well, this is if my variety is defined over K, and if my algebraic cycle is also defined over K, right? So it will give me some Galois cohomology class. And this class also can be used to detect the non-triviality of my algebraic cycle. And in this talk, I will show you direct applications of these two tools to detect non-triviality of algebraic cycles. Okay, so this is all very abstract, like an overview of the theory, but next will be do some more concrete things. Okay, to start with more concrete, let me first give you the one algebraic cycle that we want to actually work with instead of general abstract algebraic cycles. So the Ceresa cycle. So Ceresa cycle is a very naturally defined cycle. So the data you have is you have algebraic curve C, okay, and then you have a fixed point E, yeah. And if you are more sophisticated, instead of a point, you can also take a degree 1 divisor. That's fine. Okay, so then when I have a curve C and a point E, what can I do? Well, as I already mentioned, we have the Arbor-Jacobi map that embed my curve C into its Jacobian. Okay, into its Jacobian. And the map is given by taking any geometric point P on C, mapped to the divisor class P minus E, right? And so this gives me an embedding of C. Now I'm drawing this red copy of CE, I'll denote as CE inside the Jacobian variety, right? But on the other hand, there is no reason to pick the embedding as t minus e, right? I can instead map every point p to e minus p, or like the inverse of that. This choice will also give me an embedding of c, which would be denoted as ce minus. That was my blue copy. So you see that with these two different choices of embedding, I will have two different ways to embed c into the Jacobian, right? Another way to think about it is the Jacobian of a curve is an abelian variety, which means that it has a involution of multiplication by -1. So then another way to think about it is I have my embedding CE, and I compose with multiplication by -1 and get my CE minus. Okay. So now if I take the difference of these two images, I will get a algebraic one cycle inside Jacobian of C. And so this is a codimension G-1 cycle inside this G-dimensional abelian variety, right? Okay. Okay. So the point is, why do I take this difference? Right. I take this difference because this is actually a homologically trivial cycle. Okay. And the reason is the following. The reason is that, as I already mentioned, we are using complex analytic topology, which means a curve is a Riemann surface, right? So then a one cycle, if I consider the cycle class map of my one cycle CE, it gives me a class in H2. So this is 2G minus 2. Or I can more concretely literally just give you the a more concrete H lower 2. I literally have a two cycle inside a homology class, right? And then the point is multiplication by -1, this map acts as multiplication by -1 on H1 of the abelian variety. Because H1 is, so abelian variety, my complex points abelian variety is given by C to the G minus the lattice, right? And the lattice is my H1. And the addition is coming from the addition law on C, which means that multiplication by -1 naturally acts as -1 on H1 of abelian variety. And H2 is the second wedge of that. So multiplication by -1 acts trivially on H2, which means that these two classes, so CE and CE minus, will give the same class in H2. So their difference will be 0. So this is a homologically trivial cycle. Okay. And then the interesting thing is this cycle is non-trivial in the Chow group. So Ceresa, the reason this cycle is called Ceresa cycle is because Ceresa proved that for a very general curve of genus at least 3, the Ceresa cycle is non-trivial in the Chow group. When I tensor Q, I just really mean that it's non-torsion. It's not even torsion in the Chow group. It's of infinite order. Okay. So this is a very concrete, naturally constructed and very concrete cycle that we can start in. Okay. So the question I would like to discuss today is, okay, so for a very general curve, it is non-trivial, proved by Ceresa. But if I give you a very concrete curve, give you a C and give you an E, how do I tell that, or in general, how can we determine whether it's trivial or not in the Chow group? Okay, so I will first, before I go deeper into the discussion, I will give you two facts. Okay, fact number 1 is about the base point. So the data I give you was a curve C together with a base point E. Okay, so I will give you two facts and one about a non-trivial statement. So there is a case that we automatically know this cycle is non-torsion in Chow, and that comes from the base point. Okay, if my base point is not a multiple of the canonical class. If my base point E or base divisor E is not a multiple of the canonical class, then automatically my Ceresa cycle constructed from this E is non-torsion in Chow. I will explain this. Okay, I will actually give you a quick proof of this fact later on. But now let me just first tell you that if you pick so the point is, so that means this question is only interesting if you pick your base divisor E as a multiple of the canonical class. Otherwise, it's not automatically non-torsion. And this non-torsion comes from the fact that your base point you didn't choose the correct base point. So it's not about this cycle, it's about the base point. Okay, so I will give you a quick proof of this fact later, but I want you to first keep in mind that this question is only interesting, only meaningful when you pick a base point that is a multiple of the canonical class. So from now on, I will suppress the choice of base point. Since this is the only interesting question, I will always be picking a base point that is a multiple of my canonical class. And since my talk is mainly about non-torsionness, so this multiple will also suppress that. So I will just be discussing the Ceresa cycle associated to a curve essentially. Second fact I want to point out is that this cycle is trivial for hyperelliptic curve. So trivial when C hyperelliptic. The reason is the following. So in general, I get this non-trivial cycle because of my two different embeddings into Jacobian, right? But if my curve C is hyperelliptic, and if I pick a point which is a multiple of the canonical class, I can just pick a Weierstrass point, right? Which is the fixed point of the hyperelliptic involution. Then what happened is my two different embedding I told you about actually the same embedding, because the multiplication by -1 on the Jacobian, instead of mapping my CE to a different copy, what it does is it restricts to the hyperelliptic involution on CE. So you literally only get one embedding in this case when you multiply by -1. So this cycle will be 0 in this case. Okay, so okay, so the question of for which C, this is C and E, this is trivial, I give you two remarks. Remark one is if you don't pick canonical class as E, it's automatically non-trivial. And second comment is if you pick C to be hyperelliptic, it's automatically trivial. Okay, so next, let's continue our discussion. Then it is natural to ask that is this cycle trivial exactly when it's hyperelliptic? Okay, so hyperelliptic Ceresa trivial. Then does Ceresa trivial imply hyperelliptic? Well, the partial answer is that trivial in the sense of non-torsion is not enough. So there exist non-hyperelliptic algebraic cycles with non-torsion Ceresa class, non-torsion in Chao. And there are many examples now. So one of the first examples was started by myself and my collaborators, Dingbin Sango, Daniel Litt, Padma Srinivasan. And we were starting the cycle class at that point. And later on, Conglin Qiu and Wei Zhang showed that indeed, in this case, that the so-called frequent McBeast curve, this is a general 7 Hurwitz curve, is also a Shimura curve. This curve is non-hyperelliptic, general 7, and it indeed has torsion Ceresa cycle. And because this curve has torsion Ceresa cycle, then all of its quotients also have torsion Ceresa cycle, and it also has non-hyperelliptic general 3 quotients, for example. And after this work, there has been more examples. So I have listed some here, but this is currently a very actively studied topic. So there has been more results and more vanishing criteria after that. Okay.
May I ask questions?
Absolutely.
Yeah, about the things that about the oscilla which you just mentioned which is on the screen, that what can you say about the torsion?
That's a very good question. So okay, I will. Okay, maybe my my 2 or 3 slides later, I can tell you what I know. But in general, I don't. This is a very interesting question that I do want to study in the sense that what is a torsion order? So when it is torsion, what is a torsion order? So one thing I can tell you is that for this particular case, and for some of the other examples also, these were proved to be torsion because of the automorphism group of the curve. For example, as I mentioned, the frequent McBeast is a Hurwitz curve. It has a very large automorphism group. So essentially what happened is in group cohomology, you can bound, essentially you bounded your cycle, you prove that some group operation annihilates your cycle, and that group is a finite group. So you show that it's finite order, which also means that its torsion order is bounded by the order of the group. But exactly what is the torsion order. I'm very, yeah, that is something I think is very interesting. Yeah, absolutely. Okay, so yeah, so this is one thing I want to mention. Then next I want to, so how do we start this problem? As I already mentioned that essentially we need to use some linear object. We need to use cycle class, right? And I'm going to introduce the cycle class of Ceresa cycle. So the cycle class maps, Abel-Jacobi maps, you can construct them from purely abstract theory of, for example, the Ital version, you can construct it from a spectral sequence. So theoretically, you know it exists, right? But then it's very hard to actually start it. So I'm going to introduce that actually the Ceresa cycle class, you can understand it from another perspective. Okay, and this gives people another reason to start this cycle, because when I started this topic, people often ask me, why do you start this cycle? There are other algebraic cycles, right? So apart from this cycle is very naturally constructed. A cycle class also has another interpretation that makes this cycle, I think, fundamental. Okay, so I hope this will convince you why we should start this particular algebraic cycle. So namely, I'm going to tell you that the Ceresa cycle classes are related to the Hodge and Galois structures on the geometric fundamental group of the curve. Okay. So first of all, to do that, let me first convince you why we want to study fundamental groups, right? In the theory of n-abelian geometry, is that we believe that, well, we know that the arithmetic fundamental group of a curve, when the curve is a hyperbolic curve, actually determines the curve, right? So if I have a curve defined over a number field, or any non-algebraically closed field, I get a short sequence of fundamental groups. This is my arithmetic fundamental group, and the first term is my geometric fundamental group. Last term is the Galois, absolute Galois group, right? So I know that the middle term contains all the arithmetic and geometric information on my curve C. But on the other hand, how do we extract this information, right? Because it's a very complicated group, of course. So how to study that is, so in the case that, right. So one thing we can study that is by actually first let's take a look at the easier term, which is the geometric fundamental group. So let's think about the case that when my characteristic of K is 0, let's literally think about a number field case, right? Then this geometric fundamental group is, I guess I should be slightly careful. So because this is Ital, so that is the profinite completion of the fundamental group of a genus G-Riemann surface, right? It's a profinite completion of the genus fundamental group of a genus G-Riemann surface. But the point is we understand the fundamental group of a genus G-Riemann surface, right? From a graduate school topology class, we learned that this surface group is generated by A1, B1, A2, B2 until AG, BG, and the modulo is the only relation of the commutator product. So we do understand this group somewhat, right? Okay, so then consider the group ring. We can either consider the group ring with Z coefficients, or if you want to work L-adically, take the ZL group ring with a limit with L groups. Consider the group ring, and then take the augmentation ideal. The augmentation ideal is the kernel of the group ring mapping to Z. Just take the augmentation ideal. There is an ideal in this ring. Then what happens is we can consider the powers of the augmentation ideal and take quotients. Okay, so this is just purely group theoretic work. There's nothing algebraic geometry or anything there. It's just group theory. You can show that if you take the augmentation ideal modulo square, this is naturally for group. But this is very general for group. This is isomorphic to the abelianization of pi of your group. So this is H1 of C in some sense. And if you take the G square mod G cube, it naturally is isomorphic to, for this surface group case, is naturally isomorphic to the tensor square of H1 modulo the one relation you have. This is the one relation of the commutator that you came with a group. Okay. So which means that, okay, so we can form the following exact sequence of free Z or ZL modules of this short sequence. So the last term is nothing but H1 of C. The first term is given by H1 of C tensor square and the modulo 1 relation. Okay, so this is just a free Z module, free ZL module sorting sequence as of now. Which means that this sequence, of course, splits. Because I'm literally have a short sequence Z modules, it splits, right? But on the other hand, because this is a fundamental group of my curve, it not only is a free Z module, it's not an abstract group. It has extra structure. Okay, it has extra structure. Namely, it both have a mixed Hodge structure and a Galois structure. Okay, and a Galois structure. So the free Z module J mod J to the K carries a mixed Hodge structure for any K greater than 3, and this is given by Hein in terms of iterated integrals. So you can define that. And the important theorem is here. Is Harris-Pilt proved that, so I have a shortest sequence of mixed Hodge structures, right? Then a splitting is, this extension class is measured by this extension class of mixed Hodge structures. And this extension class, when I set this quotation mark equal, it means equal up to a non-zero multiple, equals to the Ceresa cycle class under the Griffiths-Arbor-Jacobi map. If you remember, Griffiths-Arbor-Jacobi map maps the Chow group to an intermediate Jacobian, and every element in the intermediate Jacobian gives you a class, extension class of mixed Hodge structures. And it is in this mixed Hodge structures extension. It's not some abstract thing. So this is what I meant by the Ceresa cycle class have other interpretations, which are also natural objects of study in general about the curve, because this comes from the fundamental group of the curve. Okay. And this Hodge class will inspire a construction called Chow-Higner points by Damon source, which I will discuss later. So I will show you that. So first of all, I told you the cycle class map is very abstract. So let me give you more content to conceptually understand this cycle class, right? But this cycle class now, as extension class of mixed Hodge structure, is still very abstract. So later on, I will make it even more concrete. I will actually show you how to visualize it. Okay. So step by step, I'll make it more concrete. So this is a Hodge theoretic sense. We will discuss that later. But for now, let's think about the Galois case. So if I'm with my degree 1 divisor, I'm just going to pick one that is over my base field. Okay. Then what happened is my fundamental group shortcut sequence, it will induce a splitting of my fundamental group sequence. And this splitting, of course, will give me a Galois group action on my geometric fundamental group. And that will make all of my augmentation ideal powers into Galois modules. Okay. And then the splitting of this sequence with respect to this Galois action, okay, is measured by a Galois cohomology class. And that Galois cohomology class, again, no surprise, is the Ceresa class under the L-adic Arbor-Jacobi map. Okay, so really, that's the work of Matsumoto. So this is like the L-adic version of Harris-Pilt. It really tells you that the Ceresa cycle class is measuring the structure of this term in the coming from the fundamental group of the curve. So both the Hodge theoretic and the Galois theoretic. Okay, so great. So how does this help us? Well, this tells us that in this Galois perspective story, right? This tells us that means if I understand the Galois action on this quotient of the fundamental group, I will be able to understand whether my Ceresa cycle was trivial or not, right? So it means that the Galois action on fundamental group actually contains the information of the Ceresa class. Okay, how do I use this? Well, in general, of course, if you give me an algebraic curve defined over Q, we don't know how absolute Galois group acts on geometric fundamental group. Absolute Galois group is huge, right? I don't know. But on the other hand, if you have a very simple, if you have a field, base field, whose absolute Galois group is simple, then we may be able to understand the action on geometric fundamental group. So in the case, now let's think about this local field, C double bracket T. This is a very simple local field because it has the algebraically closed residue field, right? So this is looks like a finite field because the absolute Galois group is generated by a single element by taking, so the field extension is given by taking nth root of T. So this is very similar to a finite field. So which means that its absolute Galois group is generated by a single element. Okay. You can think about, so you can think about this field as a family of Riemann surfaces defined over a puncture disk. And the only element in your fundamental group base is the monodrome, is going around that puncture, right? And when you go around this puncture, there will be some simple closed loops or Riemann surface that gets smaller and smaller. And if you want to compactify this family over the puncture, you will get a singular curve where it becomes a singularity, right? Okay, and so this data of this data of which loops get shrink to zero, actually, so it can be visualized as a dual graph where each vertex is okay. If I cut the loop, that becomes singular, right? And then I can draw a dual graph. Each vertex is the component, is a connected component, and each edge is the loop that I'm cutting. Okay, so this data can be put into a dual graph, which and you can think it as a tropical curve. And also this information actually contains this monodromy data because I know what my monodrome is doing. I am shrinking some simple closed loops on my Riemann surface, right? And which means that really my Galois group action is acted by the dent-twist around this set of loops. Okay, so which means when I have such data, I actually know how the absolute Galois group, the base, acting on the on a geometric fiber and the fundamental group of geometric fiber. So in this case, we actually literally know how the Galois group, the base, fully act on the geometric fundamental group. So we can use this data. It is no surprise that we can use this data to compute the L-adic Ceresa class in this case. Okay. So this is the case that where my fundamental group is very simple, it's generated by a single element, and also I can think about this family very geometrically or topologically. So in this case, I worked with Dan Corey and Jordan Allenberg. We were able to show, first of all, we were able to compute lots of Ceresa classes, and also we were able to conclude that in this case, because the fundamental group is so simple, you will always get a torsion class. We're not saying that the Ceresa cycle is torsion, but this class will always be torsion. And one reason to think about it is that the fundamental group is too small. It's like you can't, imagine you are starting Galois theory with something defined over R. Then the Galois group is just Z mod to Z, and that's all you have, right? If your Galois group is too small, then the Galois theory information is too little. Okay, so but I do want to further discuss one thing.
I'm sorry, can I ask? So
Yeah, absolutely.
C was any curve, right? Any genus, no conditions on C over.
Oh yeah, any curve. Yeah, any curve. Yes.
I also have a question about the previous slides.
Absolutely.
So this, of course, there's got to be a motivic thing in the background here, and I wonder if sort of, if that also has been worked out. If you're aware that someone has done this, that actually the the Ceresa cycle gives you the motivic extension. So when you look at the motivic Appel-Jacobi map, it does give you that motivic extension.
I know that in the recent work of Lagas Schneiderman, they discussed the motive associated with Ceresa. I'm not sure whether the question you asked had already exactly been. That's where I would look.
Mm-hmm. Okay.
Yeah.
Okay. Thank you. Yeah, because there has to be definitely.
Oh, absolutely.
Yeah.
Absolutely. Thank you. No problem. Okay. Okay, so I want to further discuss one thing, which is I want to go back to the question of Ceresa trivial and its relation to hyperellipticity. And this is also related to the question about the torsionness. Namely, as okay, so when we found non-hyperelliptic curve with torsion Ceresa cycle, people thought the question had already been answered. But I feel it's not quite, because all we know is that so there exists non-hyperelliptic curve with with torsion Ceresa cycle. But if I want to make it even more strict and I want integrally, but okay, I know this is harder because if you want to start integrally, you need to be careful with the choice of base point. Okay, but let's just think about it. So the point is, if I ask my Ceresa cycle to somehow integrally be trivial, would that be enough to tell me the curve is hyperelliptic? The reason I have this question is because in this tropical case, okay, so we computed a lot of examples, and we found that although my Ceresa class, L-adic Ceresa class, is always torsion in this case, as I mentioned, but when the dual graph of when the degeneration type my graph give a tropical curve is not a hyperelliptic tropical curve, we never get torsion order 0. For example, the following graph with edge length 1, the edge length you can think it as how fast I'm going to the boundary of mg bar. This is a non-hyperelliptic tropical curve, and we got that L-adic Ceresa class is non-torsion order 16. So we really feel that in this particular, for example, this very combinatorial problem, it seems that you only hyperelliptic tropical curves correspond to actually 0 Ceresa class. So I still think this question still holds. It's just you need this more subtle than being torsion. And following this direction, Dan Corey and I worked out a criteria to show that a tropical curve in a tropical sense, there's an invariant we constructed which is trivial if and only if this tropical curve has a hyperelliptic Jacobian. But so it is related to the curve being hyperelliptic, but we also haven't answered this question in the tropical sense. Okay, so let me move on. So finally, okay, now I want to talk about non-triviality in Chow group. Really, so previously I was talking about the torsion case, right, a little bit. So because I was discussing over C double bracket T, and the Ceresa class is always torsion. So that can't be used to show that the Ceresa cycle is non-torsion. But now I finally let's talk about the case where we want to prove the Ceresa cycle is non-torsion in Chow. So let me first review some of the previous works and current ongoing works. So we know Ceresa showed that this is true for very general curve of genus greater than 2. Now we also know why greater than 2, because hyperelliptic gives you trivial ones, right? So you need to go genus greater than 2 to be non-hyperelliptic. And then Harris Bloch showed that for Weimar curve F4. So they proved the stronger statements. They proved this non-torsion modular algebraic equivalence. Then the next work is, as I mentioned, Payman's work with Murty, where they showed Weimar curve Fp of prime p greater than 7. So this is a work really, as I said, inspired our work. And then this year, there has been many work in this direction. For example, Ziang Gao and Shou Zhang were studying non-vanishing locus of the Ceresa class cycle in MG. And then there's also still also this year's work of Hein and Kurt Tayu. And there's also ongoing work of Allenberg, Logan, Srinivasan, and Venkatesh. They are trying to construct, so they will give a algorithm, which if you put in a curve, this algorithm will certify that this curve has non-torsion Ceresa cycle. Okay, if it succeeds. Okay, so this is still ongoing. And the work I want to present today is joint work with Matt Kerr, Conglin Qiu, and Tong Haiyang. So we were working on modular curves. So we essentially showed a large family of modular curves is associated to non-torsion Ceresa cycle. And by large family, I mean we can currently show some congruence subgroup. So if we can prove this family of modular curves. So common subgroup gamma 1 of 2n intersect gamma 1 2. So really we need a full 2 torsion. Okay. For n sufficiently large. Okay. The point is, yeah, we were able to work out with modular curves. So this is the result. But really important is how to do this. So this is the okay. So really the question is how to do this. So namely, I already question.
Just a very quick question about this. Do you have control about these integer n that have large?
Oh yeah, absolutely. Oh, thank you.
Yeah. Yeah.
So this integer n is what we need is we have a concrete list. So what we need is gamma 0 of n. I need a modular form in V2 cast form of gamma 0 n minus such that is L derivative does not vanish. I will show you why. The point is I need non-trivial Higner divisor. So it's very concrete, and we know exactly how large I need to be. We have a finite list of n that any other questions? Yeah.
Thank you. That's yeah.
Yeah. Okay. Okay. So then the really important thing is how to do this. So I already told you from the Galois perspective, what you need to know to use the L-adic Ceresa class to study L-adic Ceresa class. You need to know how the Galois group acts on the geometric fundamental group. Now let's talk about the Hodge theoretic. So I learned all of this from Payman's work, really. Okay. So now the point is, I recall that in the Hodge theoretic sense, I have a short sequence. So first of all, I dualize everything to be cohomology. And now the last term is easy to understand. This is the kernel of the cup product. Okay, so we will dualize. So I want to study whether this short sequence of mixed Hodge structures are split or not, right? And that's the problem. So what you do is instead of directly starting, so this is from the work of Damon Roger Sauce. So the key idea is instead of starting this original sequence, what I do is I take a Hodge class and pull back this sequence. So I get a much simpler sequence, which is a extension of H1, same H1, and Z adjoint -1. And so the point is the extension class of the top sequence is measured by a point on Jacobian variety. So the extension class of the top thing is a classical Jacobian. And the extension class of the bottom thing is intermediate Jacobian. That's hard to understand. But the top thing is measured by a point in actual classical Jacobian. And then the top sequence non-split, of course, implies the bottom sequence non-split. Since I want to assert non-split, I just need to find a zeta that makes my top sequence does not split. Okay, so this extension class is what they call Chow-Higner divisor because they were also working with modular curve to begin with. That's why they were called Chow-Higner divisor. Okay. So next, I want to show you how to visualize Chow-Higner divisor. As I said, this extension class of Hodge structures is still very abstract. Now let me show you how to visualize it. Namely, to do this, unfortunately, we need to use a different cycle. Okay. So Ceresa cycle has its benefits. It is in the Jacobian variety, which is a abelian variety. But on the other hand, there's a closely related cycle of Ceresa that has the benefit of being a codimension 2 cycle always. So the problem with Ceresa is it's codimension G-1. So when your genus is very high, it becomes a very high codimension cycle. It's hard to visualize. Now let's introduce you another cycle. It's called Groth-Kudla Schoen modified diagonal cycle. So now I construct give me a curve C. I construct a threefold C cross C cross C. This is a cube, C cross C cross C. And then I can embed my curve C in there with the big diagonal, right? It's diagonal embedding. And I will call this copy C1, 2, 3. This is my big diagonal, right? But on the other hand, I can also embed into smaller diagonals, right? So big diagonal means I map P to PPP, right? But I I can also embed into a smaller diagonal. Let's call it C12, the phase 1, 2. What you do is I map P to coordinate 1 is P, coordinate 2 is P, last coordinate is my fixed point E. Okay, because I have a fixed point, just like a Ceresa data. Okay, then I can map it to smaller diagonals. So which means this, I get this these 7 different embeddings of C into my Q very symmetrically, right? And I do this inclusion exclusion operation. And the whole point is this linear combination is again homologically trivial. It's the same as in Ceresa. Why do I do CE minus CE minus? It's because I want to kill homology. And this alternating sum of modifying diagonals is to make the homology class trivial. And this cycle and Ceresa essentially have the same cycle class. When I see the same, again, it means differs by a non-zero multiple. And moreover, Shou Zhang proved that these 2 cycles are trivial or torsion in Chao if and only if they are otherwise. So you can work with one or the other. You are really essentially working the same cycle. But again, this modified diagonal cycle has the benefit of being a codimension 2 cycle in a 3-fold, just like lines, curves in cubes, right? Okay, great. So why does that help? Well, because I have a 1 cycle in 3-fold that's hard to study, right? What we're going to do is we're going to intersect it with a 2-dimensional subvariety in there. Yeah. And so I have curves in a cube intersect a hypersurface. Then they will intersect in finitely many points, right? Finitely many points. Then I will, and because my cube is CCC, I can project down into 1 coordinate. Now I get a degree 0 divisor on my original curve. That is a point in Jacobian. And that is my Chao-Higner divisor. So what you do is the following. Okay, so now let me actually explain it. Now you take a correspondence Z in C cross C. You take a correspondence Z, this thing, and then so Z is in C cross C, which means that Z cross C is in C cross C cross C. This is my 2-dimensional subvariety. Now I'm going to intersect with my original 1 cycle delta. So Z cross C, I will intersect with delta. Now I get points. Now I project down to the 3rd coordinate of these points. That is the Chao-Higner divisor. You can actually visualize it. Yeah. So the point is now if this divisor is non-torsion, it shows that the Ceresa or a modified diagonal non-torsion. Okay. Okay, so as I mentioned, this was really learned from the work of Payman with Murty on Fermat curves. So we are just applying it to the case of modular curves. Okay, so since I'm running short on time, let me skip some background knowledge on modular curves. Let me just spend 1 minute to see modular curves. So modular curves, let's think about x naught of n. It is a moduli of elliptic curves of degree n cyclic isogenies, right? And on a modular curve, I have some special points, namely there are points which are parametrizing CM curve. So I have a diagram of not only I have the isogeny, I have a endomorphism of a curve that's making this commute. Okay, and this type of CM points, if I take the linear combination, I can get a family of special kind of divisors called Higner divisors on modular curves. Okay, so Higner divisors. These are linear combinations of CM points on modular curve. Because I'm running short of time, I'll just say this. And the benefit of Higner divisor is that the work of Gross-Daguerre tells us that there are times I can show that my Higner divisor is non-torsion. So Gross-Daguerre tells me that special value of L function gives me height of Higner divisor, which means that when my L prime does not vanish, I have non-torsion Higner divisors. That's the key point. Is when I have some new form whose L derivative does not vanish, I obtain non-torsion Higner divisors on my modular curve. So this is what we are going to use. The reason is that's the only thing that matters is on my modular curves, I have Higner divisors, which I can tell they are non-torsion, okay? So then the reason is if I explicitly calculate my Chow-Higner divisor, okay, so my Chow-Higner divisor was previously 0 cycles intersecting in cube, given by 2 cycle and 1 cycle intersecting in cube and project down, right? I can actually explicitly compute it and realize it in C cross C instead of CCC. Instead of 3 copies, if you explicitly compute it, you can realize it in C cross C. And it is essentially obtained by the diagonal of C cross C and the correspondence Z in C cross C we use to construct this cycle. So essentially, the Chow-Higner divisor comes from this intersection points. In a curve C cross C, you intersect the diagonal with a correspondence. This is essentially what you need.
Sorry, Wanlin, could I ask in the previous slide?
Yeah, absolutely.
Do you want the derivative of the form L function of the form itself, or its base change to not vanish?
The point is because okay, thank you. That's a great question. So the point is the following. The point is, okay, my base change is the product of these two, right? So if I take the derivative, then by product rule, I have L times L prime of the twist plus L prime times L of the twist. The point is, all I care about is some non-torsion points. I don't care about which one. So I know that, so if I know this is non-zero, I can pick chi such that this thing is non-zero and this thing is 0, essentially. Sorry. L prime non-zero, L is 0. Sorry, this term is gone. All I need to pick a chi where this is non-zero. But I know such chi exists by essentially, I think I think there should be a positive density kind of congruence condition that should give me a positive density of chi that tells me this is non-zero, so that I know the base change is non-zero. Because I don't care about which chi. I just need to show the existence. Yeah. Does that make sense?
Yep. Okay,
great. Thank you. Okay, so the point is, if I explicitly calculate the Chow-Higner, actually is essentially the linear combination of the diagonal of in C cross C with the correspondence. Now let's think about the case of a modular curve. And in a modular curve, I have natural correspondences, namely Hacker correspondence, right? A Hacker correspondence. So if I take it as a Hacker correspondence, let me take a prime degree one even, then it is measuring the elliptic curve with a degree p, I sort it into a different elliptic curve, right? But what does it mean for the T of p to intersect the diagonal? Well, it means that my elliptic curve has a degree p I sorted to itself. That means my elliptic curve has Cm, right? So I know that this intersection has to be supported on Cm points. So it is a linear combination of Higner divisors, right? And if we could prove the non-triviality or non-torsionness of this linear combination of Higner divisors like Gross-Zagier, then we win. That's the ideal scenario, right? But unfortunately, we weren't able to do that. That is not how we proved our statement. Okay, we were not able to actually explicitly show the non-torsionness of this linear combination of Higner divisors. What we actually did is we prefix a non-torsion Higner divisor, which we showed exists, and then we show that I can, by using linear combinations of Hacker, I can cut out this specific Higner divisor. So I'm not showing that there exists a Hacker correspondence which gives me or non-torsion linear combinations of Hacker. But what we do is we fix a non-torsion Higner divisor and show the existence of of a correspondence that cut out exactly that thing. That is why we had to go up to this weird modular curve instead of directly work on x naught of n. So let me just spend 1 more minute to explain this. This is my last slide. So I have a prefixed Higner divisor here. I have a prefixed Higner divisor on x naught of n. Okay. I would like to construct cycles on x naught of n cross net of x of n such that if I pull back, I get my prefixed Higner divisor. Okay. And we were not able to do that. What we did is once I raised my level to not, so first of all, from gamma naught of n, we raised to gamma 1 of n. Next, we added the full 2 torsion structure. After I raised level, we were able to construct cycles here such that if I pull back, then push forward, I get my prefix thing. This is what we want to do. So we directly worked with this xn cross xn as a Shimura variety and constructed cycle there. And we were having trouble constructing cycle on x naught of n cross x naught of n. But I don't think it's the essential difficulty. It's really just we finished it, it's the end of summer and the fall semester is busy.